So in this contrast stretching, it's a point processing operation. So we are applying some function T on original pixel value R or original gray value. So we studied about this S-shaped curve of contrast stretching. So this S-shaped curve gives you relation between original gray value R and modified gray value S. And in order to implement it practically, we use piecewise linear approximation of this curve. Okay, so this piecewise linear approximation is as shown here. So basically in contrast stretching, this narrow range, input pixel value range, which is ranging here in this example from R1 to R2, we are stretching it over wider range, say from S1 to S2 by this middle line segment. By this very first line segment, we are making already dark pixels, we are making them darker. And by this third line segment, we are making bright
हाँ
pixels more brighter. Okay,
हाँ
so
बाबूजी
this is contrast stretching. I request all of
नहीं
you
पापा
to mute your mics.
वो
Mohammad
क्लास चल रहा
Raza,
है
please mute your mic. Okay, so basically by contrast stretching, we are stretching input gray values over a wider range so that image contrast is improved. Now in one special case of contrast stretching is thresholding. So if you look here, this if middle portion, if you go on increasing slope of this middle portion, maximum possible condition is as shown here, right? You can have infinite slope for this middle line segment, okay? And your first segment is aligning with zero value, and last third segment is parallel to your R axis and it takes maximum value, that is either 255 if we are talking about 8-bit images. This maximum possible gray value is 255. And if we consider continuous signal ranging from 0 to 1, this maximum possible value is 1. So thresholding is one of the special case of contrast stretching where your R1 matches with R2 and it is same as M. Okay. And S1 is 0 and S2 is 1. So in this piecewise linear transformation, when your R1 is same as R2 equal to M, S1 is 0 and S2 is L minus 1. That gives you thresholding condition. Okay, so this is graph for thresholding. Okay, so in as per this graph, if your fxy, that is R value, is less than M, you are assigning a value 0 to the resultant image pixel. And if your input gray value R is greater than or equal to M, you are assigning it maximum possible bright value in the image. For continuous signal, it is 1. Okay. So because of thresholding, basically you are converting your gray image into binary image, because after thresholding your modified image has only two values, either 0 or 1. If your input gray range is less than M, output is 0. If otherwise, that is if your input pixel value R is greater than or equal to M, output pixel value is 1. Okay. So basically this thresholding operation results into binary image. Binary image means there are only two possible pixel values, either 0 or 1. Okay. So this thresholding is special. We can call it a special case of contrast stretching, and thresholding is useful to convert input gray image into output binary image. So this thresholding is very simple operation. Hope it is clear to you all. Okay. Now let us have a look at few other piecewise linear transformations. Okay. So we studied about contrast stretching, which is also an example of piecewise linear transformation because we have used this curve, piecewise linear curve for contrast stretching. Now let us have a look at few other piecewise linear transformations. Okay, so the next piecewise linear transformation is gray level slicing, as named here, gray level slicing. Now let us have a look at this very first graph. Again, this graph gives you relation between original gray shade R and resultant gray value or enhanced gray value S. Okay, so on x-axis we have R, and range for R is 0 to L minus 1. And on y-axis, we have resultant or modified gray value, which is denoted here as S. And it also has range between 0 to L minus 1. So for all point processing image enhancement operations, please note that input gray level is in the range 0 to L minus 1. Similarly, output range is also between 0 to L minus 1. Okay, now let us have a look at this first type of gray level slicing. Okay, so as indicated here, if your input pixel has value between A to B, in that case, output pixel value uh, takes some high or some bright value. Okay, and in most of the cases, this bright value is L minus 1. So your graph will be, instead of here, your graph will be here. Okay, so it takes value L minus 1. Okay, it is as shown here. Okay, so for all the pixel values are which are in the range A to B, output S value is equal to L minus 1 or brightest value in the image. And if your pixel value R is less than A or greater than B, then this value is resultant pixel value S is 0 or a dark value as shown here. Okay, S will be 0. Okay, so it will become like this. Okay. So this is gray level slicing. So basically you are slicing the input image according to input gray value. We are slicing it into say 3 parts, or we are slicing it into 2 parts. Okay. One part is for all the pixels in the range A to B. We are assigning a new gray value, which is L minus 1. And if the pixel value original from original image, if it is outside this range A to B, new pixel value is 0 or any other dark value as it was shown in the original graph. This is known as gray level slicing. Okay, gray level slicing without background. Here background is not preserved because if the pixel values are outside the range A to B, they are assigned a new value which is 0 or any other dark value as shown here, that is S1. Okay, which is very dark as compared to the compared to bright range. Okay, so this is gray level slicing. Now I request you to compare this graph. Compare this gray level slicing graph, first graph, compare it with this second one. Compare it with second one. And if you can get something, please type in the chat box. How this second type of gray level slicing is different than first type of gray level slicing. Can you identify some similarity between these two graphs? Please type the similarity. between these two graphs? Please type. If there is any similarity between these two graphs, type it in the chat box. Is there any difference between these two graphs? Please type the difference. Okay, I'm getting few answers. Yes, Sakshi, your answer is correct. For if your input pixel value is in the range A to B, all those pixel values are assigned to a very bright gray shade. This is similarity between these two graphs. For first graph, we are assigning all the pixel values in the range A to B to a very bright value. Similarly, in the second graph, all the pixels in the range A to B, we are assigning it to very bright value. Okay, so your answer is correct. Now, what is the difference? So in first gray level slicing operation, if your original pixel value is outside the range A to B, we are assigning a dark value. We are assigning very dark value, say S1, or S1 can be equal to 0. We are assigning very dark value to all the pixels which are outside the range A to B. Okay, in first case. Now in second case, you can observe that there is linear relationship or identical relationship between R and S. So if your pixel values are less than A, your S is same as R. Right here, if you look at this portion, S is same as R. Please mute your mic.
गेला तो
गेला का? किती रिफरेन्स
Please
त्याची?
mute your
बरं.
mic.
कधी घेतलेला होता तो?
Anish, Aryan, Ainab, Yash, please mute your mics. It is causing disturbance. Okay, now we are talking about difference between these two graphs. Okay, so in this first graph, S1, all the pixels outside the range A to B, they are assigned with level 0. But in this second graph, all the pixels outside the range A to B, they are kept as it is. They are not at all modified. This line indicates identity relation. S is same as R. So if your R is pixel value R is less than A, we are following this portion, means S is same as R. Similarly, if your pixel value R is greater than B, that is if it is between B and L minus 1, we are again following similar graph where your S is same as R or original pixel value. So this indicates that in this second type, we are highlighting object of interest. Say your object of interest is taking values between A and B. We are highlighting object of interest by preserving the background. Okay, so how the background is preserved? By this identity relation, background is preserved. We are not at all modifying all other pixels which are outside the range A to B. Okay, so this is also gray level slicing, but it preserves the background. Whereas in first case, we are not at all preserving the background. All the object pixels in the range A to B, we are highlighting it by a bright value, and all the pixels outside the range A to B, we are making them very dark or 0. Okay, so both these graphs, they represent gray level slicing. But in first case, we don't preserve the background. That is, it is without background gray level slicing. And in second case, because of this identical linear portion, we are preserving the background. So this is gray level slicing by preserving the background, or it is with background. Okay. So is the difference between these two operations clear to you? Okay. Okay, so I'm getting few yes answers. So hope it is clear to all of you. So we can try to understand it further with an example. Okay, so let us consider this example. Perform gray level slicing on the following image. So we are going to consider both the cases. First case is without background. That is this case where whatever pixels outside the range A to B, we are darkening those pixels by assigning, say, value 0 to all the pixels outside the range A to B. So, okay. So let us have a look at gray level slicing without background. Okay. So whenever we are performing gray level slicing without background, your new pixel value is L minus 1 if input pixel is in the range R1 to R2. Or if your input pixel R value R is in the range A to B, we are assigning bright shade, say L minus 1. Okay. And when it is outside this range, we are making it 0. So this is your equation for gray level slicing without background. Okay. Now consider this example. This is a 3 by 3 image. And now we have to apply this transformation, that is gray level slicing without background, on each and every pixel of this image. And for this numerical, R1 is given as 3 and R2 is given as 6. Okay. So for all the pixels in the image where pixel value is in the range 3 to 6, we have to assign level L minus 1. Okay. And if it is outside the range, we have to assign gray level 0. Now, if you look at this image, this is a 3-bit image. Okay. Now, if your pixel is represented by 3 bits per pixel, please tell me what is value of L minus 1 for a 3-bit image. Please type your answer in the chat box. If you are using 3 bits to represent every pixel in the image, what is maximum possible gray value? What is the brightest gray value in the image? If we are using 3 bits per pixel. Is that difficult? This is question from digital electronics. If you are using a binary number with 3 bits, its maximum value, what is its maximum value? Maximum value that you can represent with 3 bits, it's 7. It is not 8, but it is 7. Okay. Total, there are 8 values ranging from 0 to 7. Okay. Total, there are 8 values. If all the 3 bits are 0, you will get 0. If 0, 0, 1, you will get 1. And when all the 3 bits are 1, 1, 1, you get its decimal equivalent as 7. Okay. So if you are using 3 bits per pixel, you are getting 8 different values which are in the range 0 to 7. Right. So your L minus 1 will be 7 and not 8. Okay. So maximum possible gray value, brightest gray value is 7. So according to this equation for the given example, if your pixel value is in the range R1 to R2, you have to replace it by value 7. And if it is outside the range, you have to replace it by 0. Okay. So in this example, R1 is given as 3, R2 is given as 6. We know this equation. Now just tell me what is new value of very first pixel. First pixel value is 3. So as 3 is in the range 3 to 6, now we have to replace it by 7. Now similarly, tell me other two pixel values from the first row. Please type your answer. What is the new value by applying gray level slicing without background on the given image? Type your answer for very first row. First row original values are 3, 4, 5. Tell me what is the value of modified image for first row. Yes, Aryan, Sharan, Mom, Raza, all of you have given me correct answers. So for very first row, all the 3 pixels are in the range 3 to 6. So the resultant value is 777. Okay. So for very first row, your answer is 777. Now for next second row, type your answers. For apply this gray level slicing without background on the second row and type your answers in the chat box. This is very simple operation. You have to compare each pixel value with the given range and accordingly take a decision. Yes, Aryan, Mehak, Sharan, Sakshi, all of you have given me correct answers. Very good. So if for second row, first pixel is 6. 6 is in the range R1 to R2. So we have to replace it by 7. Again, second, same is true for second pixel. So this will become 7. Now, if we look at the third pixel value, it is 7. And 7 is outside this range 3 to 6. So we have to replace 7 by 0. Okay. Now tell me the result for the third row. 1, 2, 2. What is the resultant image or enhanced image after applying gray level slicing without background? Yes, Soumya, Sharan, Sakshi, Mehak, Pranav, all of you are giving me correct answers. Very good. Okay, so for last row, first pixel value is 1, which is outside this range. So result is 0. Similarly, for other 2 pixels, pixel value is 2, which is outside the range 3 to 6. So we have to assign a value 0. Yes, Aryan, your answer is correct. All of you have given me correct answers. Very good. So this is gray level slicing operation without background. So for this input image, we are getting this as resultant image. So your final answer is as shown here. Okay. Now let us have a look at gray level slicing with background. Okay. That is this other graph, gray level slicing with background, because we are preserving the background. Okay. So consider same example. Okay. So now whenever we say it is with background, we preserve the background by using this equation. So if your pixel value is in the range R1 to R2, highlight it by maximum possible brightness value, which is L minus 1. And if it is outside the range, maintain R value as it is, means assign S with the original pixel value R. So now you have to apply this equation to the given image. Now tell me your answer for very first row, where we are applying this gray level slicing with background. Okay. So what is result for very first row? Please type your answer in the chat box. For very first row, yes, Aryan, Sharan, Mehak, your answers are correct. These 3 pixels, 3, 4, 5, they are in the range 3 to 6. So we have to highlight them by brightest shade, which is 7. So it will become 777. Then I'm also getting no. Now just give your answer for next row. Second row, what is the answer? Yes, Aryan, Sharon, Mehak, your answers are correct for the second row. For second row, first 2 pixels, they are in the given range 3 to 6. So resultant value will be 7. We have to highlight it by brightest level, that is 7. And now last pixel. Now for last pixel, this value 7 is outside the range 3 to 6. And now we have to preserve this pixel value. Your S is same as R, so it will remain as 7. So for the second row, resultant value is 777. And what is the result for third row? Few students already typed the correct answer. Yes, Sharan, Aryan, Soumya, your answers are correct. Sakshi, Mehak, all of you have given me correct answer. Now, if we look at the last row, all these 3 pixels, 1, 2, and 2, these values are outside the given range, which is 3 to 6. Now, as we are preserving the background, we have to keep these values as it is. So, with background, result is as shown here. Your first row is 777, second row is 777, and last row is 122. So with your answers, I think all of you have understood this gray level slicing with and without background. Okay, so let us move to next point processing operation. Okay, so now we are going to have a look at next piecewise linear transformation, which is known as bit plane slicing. Okay, so basically, for digital images, we usually use 8 bits per pixel to represent the image. So this is an example of gray image, which is using 8 bits per pixel. Now, in case of bit plane slicing, what we try to do is we try to represent that image in terms of bit planes. If there are 8 bits per pixel corresponding to this image, we can get 8-bit planes. Okay. So this is concept behind bit plane slicing. So basically for an 8-bit image, we can represent 0 as binary number 00000000, and maximum bright level 255 is represented by 11111111. Okay, so any number between 0 to 255 is encoded as 1 byte. The bit in the far left side, that is this location, that is known as most significant bit. All of us know that. Why this is known as most significant bit? Because it contributes maximum to the information, right? It has highest weightage. That's why it is known as most significant bit. And bit at this position or 0th position is known as least significant bit, because it doesn't contribute significant to particular pixel value. Okay, so this is your least significant bit, this is your most significant bit. And in case of bit plane slicing, we try to represent an image in terms of bit planes. Okay, we collect LSB, least significant bit of all the pixels, and we form one plane that we can call as least significant bit plane. Similarly, we collect next LSBs from all pixels and we get one more bit plane, and we continue this process up to most significant bit. We collect all MSBs of all the pixels from the given image and we get a most significant bit plane. Thus, we can represent gray image in terms of 8 binary planes, because in every plane you have either 1 or 0. Okay, so in order to in equivalent to your gray image, we can have 8 binary planes, and this is meaning of bit plane slicing. So for the given image, when we collect all LSBs as shown here, we get least significant bit plane, and we can name this as bit plane 0. And when we collect all most significant bits, we get a bit plane known as most significant bit plane. And for all intermediate bits, we get one plane. Okay, so all these are binary planes because every plane has one bit data corresponding to each and every pixel from the image. And this one bit data can take either value 1 or 0. Okay, so basically we are representing gray image in terms of 8 binary planes. Okay, so here why we do this, why we actually represent an image in terms of eight binary planes. One of the most important reason is to take advantage of binary image compression techniques. In old days, all of you know that there was a communication technique known as facsimile communication or fax. And in that technique, only binary images or text documents. Black text was written on white paper. Those documents were scanned on transmitter end and those were received at the receiver end. So those documents, they were having 1-0 data or binary images. And for facsimile communication, binary image compression techniques were used. Okay, and those same compression techniques we can apply to gray level images if we represent the image in terms of binary planes. So on every binary plane we can apply those image compression techniques and we can reduce the amount of data required to represent the image. Okay, so that is main reason why we go for bit plane slicing. Okay, so converting a gray level image to binary image is possible by bit plane slicing. Secondly, representing an image with fewer bits and correspondingly the image size can be reduced. So basically image compression is one of the motive behind converting your uh, gray image into bit planes. And we can also enhance the image by focusing only on say most significant planes. Okay, we know that as compared to least significant planes, most significant planes contribute more to each image data. So when we want to enhance the image, we can focus more on most significant planes than least significant planes. Okay, so this is motive behind representing your gray image as binary planes. Okay, so let us consider one example to understand how we can represent an image, gray image, in terms of binary planes. Okay, so for simplicity, now let us assume that your image has 3 bits per pixel. Okay, now if your image has 3 bits per pixel, how many binary planes are possible for the given image? If we are using 3 bits per pixel, how many binary planes, how many binary planes are available?